First one up is Eryk Dutkiewicz, I hope I pronounced it correctly, from here, UTS.
Armed and dangerous. So good afternoon, everybody. It's a pleasure to be here this afternoon. What I'd like to do is to give a very short sort of a sample of projects that we do on IoT cybersecurity at UTS. So I represent the School of Computing and Communications, where we do research into cybersecurity and IoT. And this is just a sample of what we would like to present to you this evening, this afternoon. I've got, I think, 10 minutes, because we're running 10-15 minutes. So if I run a bit over time, which I tend to do, stop. Okay, let me just progress this. This works. So what is IoT in the first place? I think I first heard about IoT about 20 years ago. So it's not exactly new, but it wasn't called IoT. At that time, we called it wireless sensor networks. And the guys at Berkeley came up with the concept even earlier than that, maybe in the 80s, smart dust. We are here talking about IoT 30 years later. Smart dust, by the way, is still a long way away from being a reality. But at least now we are looking at trying to make some money from some of the concepts and ideas. So we're trying to enable objects to talk to other objects. Those objects can be pretty much anything, ranging from surveillance cameras to soil moisture sensors for agriculture, medical implant devices, very wide range of possible applications. So basically what we're looking at is billions and billions of devices, which is, as our guest speaker, the keynote speaker said, another level of scalability required. So we are greatly extending the current internet. And of course, for many, many applications, security is essential. For some, not so, but for many it is. So trying to understand about IoT and security, I have a nice slide given to me by one of my colleagues, the taxonomy of security and IoT. So as you can see that you have quite a lot of different areas that you can cover. I think there was a bit of a misformatting. I was promised that wouldn't happen. So you can see that we're looking at secure production and data collection. We're looking at secure connectivity and configuration, secure brokerage, storage, and integration, and secure visualization and action. So in our research at UTS, we are looking essentially at those three areas, or some aspects of it. And in particular, today I'll show you a few examples of projects in two particular areas: secure production and visualization of image-based IoT. Don't know what happened to the formatting there as well. And secure communications for hard-to-secure devices. So basically, image-based IoT applications and secure communications for hard-to-secure devices. There are two very different types of applications. Oh, that works now.
It's the same file, I did not change it. So
maybe it's a professor has some viruses.
Yeah, I reckon that USB was doing its job. Okay, so basically, I'm going through very quickly. You saw this already, those two areas. Okay, so in the first area, we're looking at securing information inside images. So on the image on the left-hand side, we have a beautiful image of Sydney. And as you look at it, you say, well, this is just an image of Sydney. But in fact, this image contains 100 pages of text hidden inside this image, which will tell us various facts about the city. So you can see that within the image itself, you can see there's hidden texts. So we can look at particular methods of hiding text into images, perhaps coming from surveillance cameras, other information as well, in such a way that it cannot be easily decrypted. So this area is called steganography. I just learned that word a few days ago, and my colleague Dr. Zenon Hachko, who is around, he can explain to you more about the research. Another area that we're working on is on social event identification and tracking. So we all know about the events in Paris, other events in Istanbul and so on, where basically, if it was possible to predict that they would be happening, maybe they could be prevented. And there was a failure of this prediction. So what we're looking at here is basically augmenting physical information that we can get from the physical world with other information from the cyber world. So what we're looking here is basically cross-domain event analysis, analyzing information from the physical world and the cyber world, such as information coming from different types of social networks, perhaps Facebook, Twitter, and so on. Now, this is quite challenging because we have different types of information that we have to integrate, that we have to fuse, and some of it can be very inaccurate. So how do we cope with this inaccuracy? And the events we're trying to predict are also very rare. So how do we make it accurate? So we're looking at various ways to modeling it, using, for example, the dynamic sparse representation of the information. So if you're interested in more information about this particular project area, my colleague, Dr. Min Xu, who is in the audience, will be happy to talk to you about it. So there were two projects basically related to image, video, maybe IoT with video surveillance types of applications. Now we're moving into different types of devices, perhaps, devices that we are more familiar with, such as smartphones. Is smartphone an IoT device? It's a fantastic platform with sensors already. It's got lots of sensors as well. It's got a lot of power, computing power. So securing that device, maybe it's not so difficult. As we heard, Apple is trying to fight for that. Good for them. But there are many other devices which are much more difficult to secure. And we're talking about devices which have limited processing power, limited memory. This could be things like smart meters, wearable devices, different types of sensors, implantable devices such as pacemakers. They don't have the processing capability to be able to provide very high encryption or to be able to carry out decryption as well, because they will run out of power very quickly if we try to do it. So the question is, what do we need? How do we secure such devices? So one area of research we're carrying out is in terms of protocols, and this is an example of a lightweight mutual authentication scheme, which is using payload-based encryption. And this is based on a protocol that is developed by the IETF, which is called CoAP, which is basically used for devices constrained by different types of resource restrictions. So what we have done, we have enhanced the protocol by introducing a different type of authentication. When the connection is being set up, we have to authenticate. We authenticate both between, so the handshake is in such a way that we have to challenge the server and challenge the client to be able to have the connection set up. So in terms of the encryption is happening in the payload, and it's 128 bits, and this is optimized for power consumption. So if you're interested in this protocol and how it can be used, my colleague here, Dr. Priya Nanda, is in the audience, and he can talk to you about this particular protocol. So moving on with the challenges of those devices. They are unprecedented, not used to such security challenges. Before, we had devices which were very, well, they had enough power to be able to provide some security for us. Now we have different issues we had from the panel before, legal and security, privacy issues. There are concerns that data is everywhere, and we're going to be spied on by those devices. They are distributed in nature, so how do we manage a large number of distributed devices? There is nobody in control anymore. Sensors in public areas are unprotected. They can be physically stolen, for example. So how do we make sure that the information sitting on those sensors doesn't fall into unwanted hands? Devices have limited power, limited computational capability, limited storage. Wireless links, they are often wireless devices. They are vulnerable to simple attacks like eavesdropping and jamming. We have lots of passive RFID tags which can be easily read as well. So to give you an example about the challenges that we are facing is, for example, can we use conventional encryption in such devices? This is an example from a Texas Instrument-based device, sensor node, which is an example of sending basically sending 14-byte packets at a very low rate of 250 kilobits per second. For that, we require 448 microseconds of time, and it consumes about 35 microjoules of power. Now, if we wanted to put security overhead into the transmission of this packet, and we assume about the same amount of time for the encryption process, we can only afford about just over 5,000 security operations. But for the traditional TSL security protocol, we require 16 million operations. So definitely this is not possible with the current encryption. So we need some new approaches to do that. So typical threats. We have unauthorized access. Somebody can read smart meters, wearable devices, implant devices. Somebody can try to read your pacemaker and try to reprogram it. How do we prevent that? How do we prevent eavesdropping, leaking confidential information from devices? How do we prevent modification of information on those devices? So what we have here is an example of some possible solutions. So the first one is we have basically a set of sensor nodes, maybe in the field, deployed. We have a reader that's trying to read information from those sensors, and we have the little devils trying to do some harm to them. How do we prevent those devils to read our information? So what we can do here is basically the reader itself can inject interference into the signals to conceal the readings. So the reader knows what the jamming information is, or the interference information is, so the reader can detect it and decode it. Whereas the little devils, they don't know what it is, and they basically hear noise. So that's one way to try to prevent this type of eavesdropping, friendly jamming. So my colleague, Dr. Diep Nguyen, who is in the audience, I think, maybe he's on the plane to Vietnam right now, he's working in this area. Another solution could be to look at data forensics, or big data for little devices. So here we have somebody who's trying to introduce spoofing into our reader. So how does our reader know that he's being spoofed? So we can use different types of analysis. So we can look at basically anomaly detection. We can look at the information at different levels. The physical level, we can look at the signal strength readings, which may not be what is expected. We can look at the channel fading profiles, which have been now changed because of the spoofing information being introduced. We can look at the MAC level. We can look at the packet sequence numbers not being the correct ones anymore. At the traffic level, we can look at statistics of the traffic, as it is shown on the figure here. If you introduce spoofing information, the blue packets, then when you aggregate the blue packets with the green packets, the inter-arrival time between the packets now becomes much less, which is not what should be expected. So we're being spoofed. So then we can do something about it. So this is just a few examples of our projects, and if you're interested, please talk to the project leaders who are in the audience, and if you'd like to see some demos, I'm sure that we'll show you some demos as well, building next door. So thank you very much.